Imagine, just for a second, the absolute sheer chaos of being inside a structural fire. You're inside, and the heat, it's completely suffocating, pushing hundreds of degrees. Thick, toxic smoke is absolutely everywhere, blinding you, while the roar of the flames just drowns out almost every other sound. It's a raw, terrifying, literally life-or-death environment, where every single second counts. Now, in that kind of extreme chaos, you'd probably think survival is purely about brute force and, well, bravery, right? But as we're going to see in this explainer, taming that inferno relies just as much on the cold, precise rules of physics. Which brings us to a seriously fascinating question. How exactly does an 18th century physics equation actually save lives in a burning building? I mean, it seems totally wild, doesn't it? A mathematical concept scribbled down hundreds of years ago is actually the invisible hand that modern firefighters use to manipulate smoke, control extreme heat, and ultimately survive the fireground. We're literally talking about mastering invisible forces here. Okay, let's dive right into this and map out our roadmap for today. We've got 1. The physics of firefighting. 2. Controlling the airflow. 3. Cooling with fog streams. 4. The dangers of wind. And 5. Tactics and fire survival. Section 1. The physics of firefighting. Let's lay down the foundation. So before you can even think about clearing a smoke-filled hallway, you really have to understand the fundamental law that dictates how fluids behave. And yeah, in the world of physics, air and smoke, they're totally treated as fluids. So the absolute crucial point here is Bernoulli's principle. Basically, it states that as the speed of a fluid, whether we're talking about air or water, increases, its pressure decreases. It's a direct inverse relationship. Velocity goes up, pressure goes down. Keep this incredibly simple rule locked in your mind because this one single dynamic is the key to basically everything we're about to look at. Section 2. Controlling the airflow. Let's talk ventilation tactics. Let's pull this right out of the textbook and put it directly on the front lines. When crews pull up to a blazing structure, one of their absolute top priorities is ventilation. They need to clear out that blinding, toxic smoke so they can actually see, and more importantly, so victims can breathe. So they use these massive, high-velocity fans to manipulate pressure differentials, but they can do it in 2 completely different ways. First, there's positive pressure ventilation, or PPV, which creates a forceful flow straight through a structure. On the flip side, you've got negative pressure ventilation, or NPV. That's where exhaust fans are set up in a window or door to pull the smoke out. With NPV, the fan speeds up the exhaust flow, and that creates a lower pressure zone that literally sucks the inside air right toward it. But let's zoom in on PPV for a second, because the mechanics here are just fascinating. The fan blows this high-velocity air, and remember our principle. That high speed actually lowers the air pressure immediately in front of the fan nozzle. So here's the chain reaction. Higher pressure air from behind the fan gets drawn into this new low-pressure zone, creating a massive controlled wave of airflow. The effect? It forcefully pushes the heat, the smoke, and all those toxic gases right out of a strategically chosen exit downstream. You're literally creating a clear, breathable path for survival. Section 3. Cooling with fog streams. Time to manipulate some water. Now, physics doesn't just apply to giant fans. How does a fire hose actually cool a room down? Believe it or not, it's not just about getting things wet. When water's forced through a tiny fog nozzle, its velocity shoots way, way up. Following Bernoulli, this fast-moving water creates a low-pressure zone right around the stream. Step 2. All those surrounding superheated hot gases and steam are literally sucked or entrained right into that low-pressure water stream. Step 3 is where the magic happens. Intimate mixing. The heat energy transfers incredibly fast to the water droplets, rapidly cooling the gases below their ignition point and turning everything into this huge blanket of smothering steam. It actively stops a flashover dead in its tracks. But we have to be realistic and look at the complete tactical picture here. Because that entrainment effect is so incredibly powerful, a fog stream can sometimes actually push the fire away from you, making it really tough to get water directly onto the burning solid fuel itself. So for those deep-seated fires, firefighters often have to switch over to smoothbore or straight stream nozzles. That gives them much better penetration without that massive pressure-sucking effect getting in the way. Oh, and there's another really cool, though somewhat limited application of this: water curtains. Firefighters can spray a high-velocity sheet of water to shield an escape path or protect an exposed building right next door. This fast-moving water naturally creates a low-pressure zone, and when you combine that with the Coanda effect, which is basically how fluids naturally want to follow a surface, Bernoulli's principle helps entrain the air, theoretically deflecting that intense, blistering radiant heat right away from the crew. Section 4. The dangers of wind. Unintended airflow. All right, we need to flip the narrative for a minute here, because the exact same physics principle that allows crews to clear a room and cool lethal gases, it can turn instantly deadly if it's misunderstood or just ignored. Imagine a strong wind howling across a broken window or an open front door. That wind is drastically increasing the air velocity right over the opening. Bernoulli dictates that this creates a zone of lower pressure right outside. And this low pressure, it acts exactly like a vacuum. The higher pressure air and smoke inside the building aggressively flow outward toward that low pressure zone. This draws massive amounts of fresh oxygen right into the fire on the upwind side, violently intensifying the flames and driving incredibly rapid fire spread. And this brilliantly illustrates a golden rule on the fire ground. Every opening affects pressure and airflow. An uncontrolled door, a completely smashed window, or a breach in a wall, it isn't just a hole. It's a dynamic valve that completely alters the velocity and pressure of the entire structure. One single uncontrolled opening can totally dictate the behavior of the entire fire. Which brings us to a very stark warning: the backdraft. If a fire has consumed most of the oxygen in a superheated room, just opening a door creates a massive, sudden pressure differential. Oxygen absolutely rushes into that oxygen-starved space, mixing with those superheated gases. Driven entirely by these sudden pressure and velocity changes, the result is a catastrophic, explosive ignition. Venting a room without extreme caution is literally deadly. Section 5. Tactics and fire survival. Applying the physics. So how do we take all this invisible, fluid dynamic stuff and translate it into actual, actionable rules for the people wearing the gear? Well, here are the essential takeaways. Number 1. You absolutely must coordinate ventilation control. Manage those openings. 2. Place that PPV fan strategically so it's purposefully pushing air into an inlet and out a designated exit. 3. Direct your fog stream overhead into the hot gas layer to get the maximum cooling entrainment. 4. Fiercely respect the wind direction. Always try to attack from the upwind side if you can. And finally, always beware of creating new airflow paths when you're opening doors. But of course, we have to acknowledge the messy reality of the fire ground. A burning building isn't a pristine science lab, and air and smoke aren't perfect, ideal fluids. You're dealing with crazy turbulence and massive temperature differences. While Bernoulli's principle heavily drives the horizontal airflow near openings, we also have to factor in thermal buoyancy, the stack effect, which is just the fact that hot gases naturally rise, dominating vertical movement. A firefighter constantly has to balance the mechanical force of their fan against the natural, heat-driven ventilation of the fire itself. So, to wrap this all up, understanding velocity and pressure isn't just some abstract science lesson to memorize. Bernoulli's principle is an absolutely essential tool in a firefighter's mental toolbox. It's what allows them to predict airflow, cool down hazardous gases, anticipate those scary wind-driven dangers, and make informed, life-saving decisions on the fly. They aren't just fighting fire with water, they are actively working with physics to control their environment. It really completely changes how you look at the world, doesn't it? The exact same physics keeping a massive airplane up in the sky are saving lives in some of the most extreme, chaotic conditions on Earth. Are you ready to see the invisible forces shaping the world around you? For more, visit our website, Fair Solution.